In video 2, we're going to talk about what makes something a strong acid versus a weak acid, and what makes it a strong base versus a weak base. Okay, so if we look at the table here up top, we have the strong acids listed. HCl, sulfuric acid, and nitric acid are just 3 of them on this list, and they're designated as strong acids because they completely dissociate when they go into water. And what that means is that if I have HCl and place it in water, I'll get a single arrow going in one direction to give me the hydronium ion plus Cl minus. So it completely breaks up. The chloride ion that we generate, the conjugate base of this acid, really doesn't want anything from water. It doesn't want the H+. It's a spectator ion kind of freely floating around in there, and for that reason it makes it a strong base when your conjugate doesn't want anything from the water. So if you remember back when we were learning about naming acids, we were talking about the different strong acids, and we have HCl, hydrobromic acid, so hydrochloric acid, hydrobromic acid, hydroiodic acid, nitric acid, sulfuric acid, and perchloric acid are the 6 strong acids. And you have to remember all of those. And the good thing about remembering those 6 is every other acid that you encounter is going to be a weak acid. Okay? So what they do is they completely dissociate in water, and if I know what the concentration of that acid, especially if it's a monoprotic acid, let's say I had 1.25 molar hydrobromic acid. Because of that one direction arrow, it's completely dissociated. I can say that I also have 1.25 molar hydronium ion concentration. Right? And this will be important when we're doing calculation of pHs. So if that HBr, this concentration 1.25 molar, is in water, it's also 1.25 molar in hydronium ion concentration. Okay. So again, we have its dissociation in water is complete. It's one direction. And the Cl minus really doesn't want anything. The equilibrium lies way, way far on the right, and we designate that as a single-headed arrow going in that one direction. Okay, so weak acids are everything else on that list, and here are some of them listed here in the table. And now the conjugate bases that they generate when they dissociate, when they give up their proton, they actually want something from water, and I can't draw that straight arrow, that one direction arrow, showing only products being formed. We can see that on the next slide. So something like acetic acid, when it goes into water, I have to draw equilibrium arrows because it's not completely dissociated into hydronium ion and acetate ion. Acetate actually wants something from water. It acts as a base if I were to throw it into water. So in the presence of acid, it will react, and I'll get that reverse direction. Remember, the amount of reactants and products is determined by K, and for this reaction it's somewhere in the 10 to the minus 5 range. So it heavily favors the starting materials. Very little bit of it dissociates to hydronium ion and acetate ion. So the equilibrium favors the left-hand side of this reaction. Okay. Then we have some other substances that really don't dissociate at all. I mentioned hydroxide in class once or twice. Imagine hydroxide in water giving up its H+ ion. That would give O double minus, which is really a superbase, right? So in homage to Nicki Minaj, we'll call it a superbase. Things like H2 will give H-. That's a superbase. These things are super, super strong bases, and in water they just don't happen, right? Generating a methyl group and taking that, just having methane deprotonate to give the methyl anion. Just not going to happen in water. That's way too strong of a base, and it'll react with water instantaneously. So we're not going to get that dissociation, and these things aren't acidic at all. because their conjugate bases are such strong bases. Okay, so the strong bases we have to remember as well. We have the group 1, the alkali metals, so lithium, sodium, potassium, rubidium, cesium, and francium. All of these are strong. They form strong base hydroxides, as well as calcium, strontium, and barium. Remember, all of these form the +1 cation, and so they'll make a 1-to-1 mixture with the hydroxide. Okay, and again, they dissociate completely when we throw them in the water. So if I had sodium hydroxide, again, I'll have that one direction arrow. That'll give me sodium ion plus hydroxide ion. It's 100% dissociated. The sodium doesn't want anything from the water. It's a spectator ion floating around, and when this dissociates, I get completely the OH minus, and that's what makes it the strong base. Weak bases are everything else. All right, so ammonia is an example of something that behaves as a weak base when it reacts with water. Now, water in this reaction is behaving as the acid. I get the conjugate acid, which is the ammonium ion, and I get the conjugate base hydroxide. So bases, according to the Bronsted-Lowry definition, are lone pair acceptors. They accept that hydroxide. To be an Arrhenius base, it has to increase the hydroxide ion concentration. So it actually is an Arrhenius base as well, ammonium, right? It doesn't directly give hydroxide ion in solution, but when it reacts with water, it does. It produces it as its conjugate base.